So having discussed the Atwood's machine problem, let's do another standard problem by using Newtonian approach by the method of free body diagrams. So this is the carriage problem, or also known as railway carriage problem. So here you can see I have taken or I have considered three connected bodies having masses m1, m2 and m3. So let's consider them to be some sort of what do you call railway carriages. Now they are all connected by some chains or strings which is able to transmit some tension. So let's assume that the system is pulled towards the right by a force F. So let F be the force with which the system is pulled towards the right. So means maybe you can imagine that there is a locomotive engine, okay, engine of the train which pulls it towards the right. I have shown m1, m2, m3 of different dimensions, but it can be of the same dimension but different masses due to the loading effect on it. But okay, so let's say this is the system. Now our aim is, once you are pulling it towards the right and we say neglect completely the friction, we neglect the friction on this track. So in order to show that, we are showing this track to be shaded. Means I think why do we show it shaded. What's the logic behind this shading? It's okay, that is another way of showing or drawing a mirror, right? A mirror is very smooth, so it's just a representation of showing that it is very smooth like a mirror, or neglecting friction. You are supposed to neglect friction. That is the that is the meaning of drawing it like this. That's a very common technique used in textbooks. And of course I have shown this is connected with some wheels, and since rolling friction is lesser than sliding friction, that also is just shown to show that you can neglect friction, nothing else. Okay, you can just neglect all these minute details in order to appreciate a problem maybe that is helping you. Yeah, so let's do the free body technique. So in order to do that, you need not draw a separate m1, m2, m3, but I can do it on the same problem, same diagram. So it is F is towards the right, that will be the resultant force, right? So the direction of the acceleration of the system means m1 plus m2 plus m3, you can consider as a single system having total mass equal to capital M, right? So let's say that let the total mass M be equal to m1 plus m2 plus m3. If you consider it, so you are applying a force F, there should be an acceleration, right? So F should be equal to, I'm writing the magnitude relation, F equal to m into A, small letter A or capital letter A, doesn't matter. So A is the resultant acceleration, F is the net force that is acting on the system, right? So for the system there will be an acceleration A, and since all the bodies m1, m2, m3 are connected together, this same acceleration will be shared by all the three objects, okay? So let's say that A is the common acceleration. And what will be the direction of common acceleration? The direction of common acceleration should be same as that of the resultant force F acting on the system, that is F. So I can say the acceleration of this body or this connected bodies will be along the direction of the force which pulls it, so A, right? So our aim is to calculate what is the acceleration of the system. So it's quite simple, okay. And also let me add one more task for us. There are some ropes or chains which connects these carriages. We have to calculate what is the tension that connects. So will the tension be the same between m1 and m2 and m2 and m3? It will not be the same. That is logically the thing, okay? So of course the tension between m2 and m1 will be greater than the tension on the string between m3 and m2. The reason also you can understand, okay? We will numerically calculate that. So let me for the time being, let me name the tension between m1 and m2 as T1, and the tension between m2 and m3, let me name it as T2. magnitude of the tension. Tension is transmitted through the rope or through the chain. So let me denote the direction. Yeah, how do you denote the direction? Say, as far as M1 is concerned, the direction of T1 will be away from it. As far as M2 is concerned, the direction of T1 will be also away from it, because we have seen our basic idea. Tension always pulls the body, it never pushes the body. Similarly, tension T2 between M2 and M3 will be pulling M3 towards right, giving it an acceleration A. But the same tension will be pulling M2 backward. Okay, it will be pulling M2 backward. You can understand it logically, also you can understand it. You imagine that this particular string, let me say this is string 2 and this is string 1 or rope 1. Suppose string 2 is cut from here. Suppose it is cut from here. Can't you imagine that it will be easy for M2 to move under the action of F, because it need not pull then M3 along, is it not? So as far as M2 is concerned, M3 is a burden, because when M2 is moving towards the right, then it has to pull along with it M3 also. So what is the effect of M3? It's just like M3 is pulling M2 backward, is it not? M3 is just, that is the effect that is on M2. M3 is pulling on M2 backward through the tension T2. That is why T2, the direction of T2 on M2 is taken to be away from T2, sorry, away from M2. Same thing when you consider the tension, direction of tension on M2 and M1 also. So just have that logic. Please spend a little bit of time on it. If you are not comfortable with this idea, please contemplate on it, think on it. So that is the direction of tension. Now it's quite easy, right? Okay, so you can just solve the problem. So let me write the equation of motion for M1, M2 and M3 separately. That is a method. So your aim here is calculate A, calculate T1, calculate T2. So I'm giving you 3 tasks. To do this one, we will be doing the free body technique. So for M1, can't you write? Okay, what is that? What is the Newton's equation of motion? F net on the body is equal to mass of the body into acceleration. This is our guiding equation, okay, which will be applying for each individual mass. So for M1 I am applying this equation number 1, let me say. Okay, for M1 F net, what is F net? There is a force towards right, that is F, and there is a force or tension. Tension is another force. Tension is a pulling force transmitted through strings. So T1 is the force that is towards the left. What is the net force? Net force will be F minus T1. F minus T1. For M1, the equation of motion is F minus T1, and that is F net equal to M into A. M is M1 into A is A itself, acceleration, common acceleration. So that is my equation number 2. Okay, you know why I have taken F minus T1? Because the resultant acceleration is taken to be towards the right. So the net force on M1 should be towards right. It is possible only when F is greater than T1, otherwise it will not move, right? So now for M2, let's write the equation of motion. What do we write equation of motion? Let's analyze the various forces acting on M2. What are the forces? One is T1 that is acting towards the side, and other one is T2 which is acting away from it. So what is the net force? Net force will be the difference between T1 and T2, and which should be greater? Certainly T1 should be greater than T2. Why? Otherwise there will not be a resultant acceleration towards the right. So acceleration here is towards the right, and the direction of acceleration is same as the direction of the net force. So the net force is towards the right, so T1 is greater than T2. That is the idea. So I can say for equation that is T1 minus T2 is equal to M2 the mass, M2 into A. That is my third equation. Similarly, you can write for M3. For M3 it's quite simple because there is only one force acting on it, neglecting friction and all. Okay, so what is that? I can say the net force is only T2. So T2 is towards the right, so acceleration is also towards the right. It is A, so T2 is equal to simply m3 into A. That is my fourth equation. See, let me ask you one question. Okay, may not be relevant. Is there not any other forces acting on all these systems? Of course there is. What is that? Yeah, there will be weight m1g acting here, vertically downward, but there is it is getting cancelled due to the normal reaction R1 or n1. That is why there is no vertical movement. Similarly, there is m2g acting downwards. You might have done all these things in your lower classes. So there will be a normal reaction R2 here, which cancels. And there is m3g acting here. We are neglecting all these things, remember, okay? And there will be a normal reaction R3 here. So they are always getting cancelled. So that is why the net force we are taking as T2, T1 minus T2 and F minus T1, neglecting all these cancellations, okay? So have that idea. Okay. Maybe that these things may not get cancelled in a slanted plane problem. Be very careful about it. Okay, there will be some component of the weight, okay, that remains, or normal reaction that remains not cancelled. Okay, be careful about it. Yeah, so you got the three equations of motion. Now it's a matter of okay, just solving it. So what you can do is that you can just okay, if you have to get the acceleration, you can get rid of T1 and T2. How can you get rid of T1 and T2 from here? You know, there's minus T1 plus T1 minus T2 plus T2. So the simple technique is that you add this not. So 1 plus 2 plus 3, right? 1 plus 2 plus 3 will give you, or T1, T2, T3 will get cancelled out, right? So T2 and minus T2 cancels, T1 and minus T1 will get cancelled. So what remains only is F. So F on the left side is equal to, right side you have got simple thing like, so A is common there. So it is M1 plus M2 plus M3, and it's quite interesting, into A. So it gives you acceleration A is equal to simply F divided by M1 plus M2 plus M3. And you can logically confirm that this equation is correct, because this is nothing but what we are written here, right? Is not this equation, is not acceleration A equal to, from this equation you will get it, is not, by considering M1 plus M2 plus M3 as a single object. Okay, so just consider this M1 plus M2 plus M3 as a single body having mass capital M. Okay, so the only force which is acting, external force that is acting, is F. All T1, T2 are internal forces and they cancel away in that sense. That is a power of Newtonian method. Okay, so here from this equation itself you will get A equal to F by M, and this capital F M is nothing but F by M1 plus M2 plus M3. Is it not quite simple? Same equation only you got by the free body technique, right? Then why did we go after? Because okay, we are interested to know the tension as well. That is all the reason. Okay, so acceleration will be equal to total force by, or net external force divided by total mass. That's quite simple. Okay, now we have to calculate T1, T2, T3. So once you have got acceleration, can you use equation 4? So equation 4 will give you, what is equation 4 giving you? 4 gives you tension T2. What is T2 equal to? T2 equal to M3 into A. So M3 is what? M3 is into A is F by, so it is M3 into F divided by total mass, right? A by, so M1 plus M2 plus M3. So that is giving you T2. Once you get T2, can't you calculate T1? Okay, so what you can do is that you have to get T1. So to get T1, what you do? You just add 3 and 4. So 3 plus 4 you do. So what will be 3 plus 4 giving you? When you add 3 with 4, T2 and T2 minus T2 will get cancelled. So you will get T1 equal to. So T1 is equal to, from that equation will be getting M2 plus, right, M3 into A. That is T1. And can you substitute for A? A is nothing but F by M1. So this is A. Let me say this is equation number 5. This is equation number 6. Okay, so using that, so it is M2 plus M3, right, into A. A is nothing but F divided by M1 plus M2 plus M3. Sorry, M3. Okay, so that is equation number 7. So you could calculate all the required quantities Common acceleration A, the tension T1 and the tension T2 all are calculated by the free body diagram. Here also just understand one thing, we followed the vectorial method. This is what I want to stress. The Newtonian method is a vectorial approach, where in order to solve the problem you need to know the directions of various forces acting on the body. Otherwise you cannot write these equations and solve for it. Okay, so these are simple problems. That's why you are able to easily identify what is the direction of tension. It was not so time consuming and all. You will see that these problems can be solved by using analytical method without the pain of understanding, without the pain of bothering about the direction of quantities, because that is an energy or a scalar approach. Okay, right. So before we end up this session, let me give some insight on this problem. In all these problems you can see that the tension, common idea. So you look at T1. Look at T1. What is T1 equal to? M2 plus M3. What is M2 and M3? This is M2 and this is M3, right? M2 plus M3 divided by M1 plus M2 plus M3. M1 plus M2 plus M3 is the total mass. So what is M2 plus M3 as far as this first string is concerned? That is the those are the total mass being pulled by that string, right? That is a total mass being pulled by that string. String number 1 is pulling M2 and M3 together, whereas string number 2 is pulling only M3. So you can see that tension T2 equal to M3 into F. M3 is which one? The mass which is being pulled by T2, right? So T2 should be strong enough to pull M3, whereas T1 should be more strong so that it is able to pull both M2 and M3. That is why I told you T1 is not equal to T2. T1 is not equal to T2. That is something very, very important. Okay, so you have to use a stronger rope, okay, which should pull what? Greater mass. And in the railway carriage there is no such issue and all, you know, because all the connections should be what? Equally strong. Usually they keep equally strong. They are all uniform. The reason is that okay, there are several reasons. Okay, one is in the ease of manufacturing. Other thing is that, you know, the same carriage will maybe pushed or pulled, right? Push-pull trains. Okay, one time the engine will be in the front and other time the engine will be what on the other side. So you cannot decide which the rope has to pull with more force and has to just sustain more weight and all. Okay, so that is just a matter. And so you can generalize the tension here. The tension can be, see, tension in the string will be equal to, we can say, mass behind the, see, tension T is equal to, this is a common thing, mass behind the string or mass being pulled, mass behind string. These are some techniques, divided by total mass. This is the general equation that you can always understand or remember, times the force into force. So this is a general equation for tension in carriage problems as a shortcut method. You may forget about all these equations, but always remember tension is equal to mass behind the string divided by the total mass into force, where acceleration is equal to net force by total mass. So it's quite simple. So that's about the second approach to remind you or for revising the Newtonian or the vectorial approach. Okay. And I conclude the session for today here, and next day we will begin our discussion of analytical mechanics by first discussing the basic terminology that is being used in the topic. Thank you.